In the last lesson, we learned what inverse functions were, functions that undo another function. We also determined or calculated the inverse function for various functions. One thing we didn't answer, though, is do all these functions have inverses? Is there always a function that can undo another function? So we're going to talk about that today, whether inverse function actually exists for a given function. So here we have a function. Let's go ahead and find its inverse. To find its inverse, we go step one, we change it to y notation. We flip-flop the x and the y. And then in this case, we just have to square root both sides. And once we square root both sides, we will know our answer. Now, remember, when we square root, though, we always get plus or minus. And so this, according to everything we did yesterday, would be our inverse function. However, I would argue, and we will see, that this is not a function. Well, it is an inverse. It's not a function, so the inverse loses some of its usefulness. So, for example, if I say find the f of 2, we would just calculate it by substituting in the 2, and we get 4. Now let's try the f inverse of that 4, and it should give us back the 2. But instead of just giving us back the 2, it gives us plus or minus 2. So if we just used the inverse and didn't know what the original function was, I would know what the original number substituted into that function was. So in this case, I don't know if the plus or 2 gave me the 4. Now, I can see, because I actually did the math, I used a 2. But it could have just as likely been a negative 2, because negative 2, if you square it, is also 4. So this inverse is not a function because it gives two possibilities for the output, and functions don't do that. In fact, we had a test functions. The test we had for a function was, does it pass the vertical line test? Okay, here we do have a function. It passes the vertical line test. Over here is what we thought was the inverse function, but you can see the graph of the inverse function does not pass the vertical line test. Therefore, this is not a function, and we should never use function notation for something that is not a function. Now, one of the things we can do is we notice, because of the way a function and its inverse works graphically, and we've seen this now a few times. On the graph here over on the left, I'm actually going to draw this inverse equation. But first, I'm going to draw in the line y equals x. The line y equals x, if you recall, we've seen it, goes up 1 over 1, up 1 over 1. And if you recall, inverses were reflections in this line. And so our inverse just looks something like this and something like this. So you can see it's a flip of the original function over this line, y equals x. Now, what's important to note here, and what we're going to exploit, is the fact that, yes, we started with a function here and ended with a non-function, and it turns out that we could have predicted that the inverse would not be a function ahead of time just by looking at the original function. Because if this function doubles up like this, when you turn it on its side, it's going to automatically flunk that vertical line test. Now, we actually have a rule for this, or another method to determine if a function has an inverse. That method is called the horizontal line test. And what the horizontal line test, it's very similar to the vertical line test. Okay, this first of all is a function in red here, f of x equals x cubed plus 1, passes the vertical line test. And then if you test it with the horizontal line test, if a horizontal line only hits it in one point, then it will have an inverse. And again, I'm going to try to sketch in that inverse so you can see it. But you will see that it passes the vertical line test. So the inverse looks something like that. Comes away like this, curves in a little bit. So the inverse looks something like that. But certainly that passes, I didn't want to erase there, this certainly passes the vertical line test. So I am guaranteed that f of x equals x cubed plus 1 has an inverse function. Over here, I've got this bigger polynomial, and here I've graphed it. This is certainly a function, passes the vertical line test, but it would flunk or not pass a horizontal line test. A horizontal line can be drawn that hits it in 2 points. There's many places we can draw a horizontal line that hits it in more than 1 point. But what this says is this does not have an inverse function. And it clearly wouldn't when we think about it, because if we were to flip this about that line y equals x, I'm not even going to attempt to draw this, but it would get flipped in this direction, and that would flunk the vertical line test. So before we even try to or even find the inverse function, we can test to see if it will have an inverse. We just have to use the horizontal line test on the original function. So let's look at this in use. So here I have a function f of x equals 2x cubed plus 1. I've gone to Desmos and I graphed it, and I check, does it pass the horizontal line test? Yes, it does. A horizontal line hits it in 1 point, so this does have an inverse function, and so now we'll go about finding it. Now, your book does a particular thing where even if it doesn't have an inverse, you're still going to calculate it. It just won't be a function at that point. And so I've exchanged x and y. I'm going to slowly now solve for y. So I subtract my 1. I'm going to undo that multiplication before we do any cube rooting. X minus 1 over 2 equals y cubed. Now we can cube root both sides. Now we don't get plus or minus when we cube roots, only when you square root. So on the right-hand side, the cube root of y cubed is just y. And on the left-hand side, we have the cube root of x minus 1 over 2. That's an okay answer. And for right now, that'll be just fine. Ideally, we would rationalize that denominator, because if we separate these two, or this radical like so, that 2 is a radical in the denominator, or the cube root of 2. So technically we should fix this. Now I can't take it times just one other 2. I need to have 2 more 2's because we're doing cube roots. So I want to take it times a 4, because 2 times 4 is 8, and 8 is 2, 2, and 2. So we end up with probably our simplest answer, 4x minus 4. So I've taken this 4 and just multiplied it by everybody in there, all over, and in the denominator you get the cube root of 8, which is just 2. Now I believe our book, and I'm going to double check this real quick. Yes, I did. I just checked it. Yeah, your book is leaving it like we found it here in green. They aren't going that extra step. So certainly I would stop right there without simplifying the radical. I can only guess that they did it here just because this numerator is pretty complex. It's not just a single term, it's 2 terms. But generally you would go that extra mile. Let's do another one here. Let's see if this guy has an inverse function. Now, to find out if he has an inverse, I'm going to have to graph him. So to graph him, I'm going to pull out Desmos here. There it is. And you'll have to do this on your iPad, or you can graph it online. And so I'm just going to graph, you could use f of x. I'm just going to use y because it's easier. 2x squared minus 5. Now this graph should not be a huge surprise to us. And the reason it shouldn't be is because this is an x squared equation, and x squared equations make parabolas. But once we look at that, and we can see it, and it crosses down there at -5 for a y-intercept, we can tell this is going to fail the horizontal line test. So the inverse of f of x will not be a function. So inverse is not a function. Let me just sketch that graph for you real quick. It looks something like this. This -5 slid it down by 5. This 2 in front of the x squared makes it pretty narrow. So the parabola looks something like that. But it flunked that horizontal line test. And so this function does not have an inverse function. But we can still go about seeing why that is. And so you still have to do the calculations. Flip-flop our x and our y. Oops, I wanted black there. And let's see here, we'll add our 5 to both sides. We'll divide by 2. And here's why it is not a function. When I square root both sides, I get y equals plus or minus the square root of x plus 2 over 2. And again, our book is stopping right there. So that's the inverse of this function, but the inverse is not a function. So again, it would always give us 2 answers every time we tried to evaluate it. Last one here, let's go ahead and graph him. I have no idea what he's going to look like. He's a square root function. So let's go ahead and throw him in here. And we just type it in like normal. We can use y equals. And we'll put -3, and we'll do the square root. Now you have to be a little bit careful when you put it in there. I want 4x minus 7, the whole thing divided by 3. So you're going to have to put parentheses for x minus 7. Then end your parenthesis, then divide by 3. And you'll see now underneath that radical, I do have the appropriate quantity, 4x minus 7 over 3. And so let's take a look at this graph here. You can see that he is certainly going to, certainly a function. He passes the vertical line test, and he passes the horizontal line test, because a horizontal line would only hit it in one point. So f of x is going to have an inverse function. So I'm going to draw a quick sketch of him over here. And he looks something like this. And he does have an inverse, and we can approximate what that inverse looks like. The inverse, we'll do something like start there, and let's see if we can get him to go in the right direction. He'll go something like that. There we go. And so he'd flip over and land on that black line if we folded on that dotted line, y equals x. And clearly that green function that represents the inverse is a function, passes the vertical line test. So let's go about finding it. Y equals -3 square root or x minus 7 all over 3. Let's exchange our x and y. Just be careful here. You don't change anything else. And now we go about the business of trying to get y by itself. Well, let's undo this multiplication out front first. So we're going to divide by -3. We'll get x over, let's divide away that -3. And so now we just got the square root of 4y minus 7 over 3. Now the radical is by itself on the right-hand side. So let's go ahead and we will square both sides to get rid of the radical. See if we can move some of this. Nope, won't let us. So I'll squeeze it in on a block here. And so once we square both sides, we square the x and we square negative 3, and we're done with our radical. Now I don't like all these fractions here, so we're going to eliminate fractions. I'm going to multiply both sides times 9. 9 over 9 would cancel, so now I've got x squared equals. Now 3 goes into 9 3 times, so I have to take this entire numerator times 3, giving me 12y minus 21. And we're almost there. We'll add 21 to both sides. And we'll finally divide by 12. X squared plus 21, all divided by 12. And we can write this as f inverse because it passed, the original function passed the horizontal line test. Now, there is a slight problem with this. If you look at this equation here, note that this is, quadratic. Okay, and we just looked at a quadratic equation, and quadratic equations look like this, if you recall. And they don't have inverses. So something must be wrong because we just said the original function has an inverse, and so it should work in both directions. The inverse has an inverse, and that's the original function. Okay, so let's take a look at this graph and see what's going on. Now we've got the graph, hopefully. There we go. Will it just move that? See if we can. Nope. Ungroup all that. Yeah, move that part. And we moved our stuff. So there we go. So this is actually what you're seeing up here in the green, the part that I drew. But I didn't draw the other half of it. And I didn't draw the other half of it because then it wouldn't be this mirror image of the original function. So what this means is my domain, if you look at the green line, the part that I want, has to be just x is less than 0. So even though we found this function, this inverse function, we have to modify it just a little bit at the very end. And all we have to say is, yes, this is all true, but this is only true as long as x is less than or equal to 0. And that gets us that left-hand side of the graph up there. So this would be our best answer for this function with this domain restriction on it, so we didn't get the entire parabola. All right, that's a pretty deep thought right there. I still want you, let's look at the homework. Okay, find the inverse and determine if it is a function or not. So what I'd like you to do, and let's go ahead and do number 1 here, is you can go ahead and find the inverse first, or you can graph it first. I'm going to pull up Desmos, and this is what you're going to do. Pull up Desmos. Let's graph this guy. Y equals. It doesn't take very long to graph them. Let's see here. I got to do x cubed. And then minus 1. So there's your graph. As far as what you show then on your paper, it doesn't have to be super elaborate, okay? But just draw a quick sketch of it. Make it neat. Doesn't have to be, even though it's just a sketch, doesn't have to be ugly or anything. So we got a quick sketch of it. Yes, it has an inverse function. Or yes, inverse is a function. How do I know? Because the graph of it just passes the horizontal line test. Then we go about finding it. Again, not too many steps. We switch our x and our y's, take our 1 over, and I cube root both sides. Again, with cube roots, you don't have to do plus or minus. It's just cube root of x plus 1. You don't have to graph the inverse. You just have to verify it exists as a function and then find it. If the answer is no, you still want to practice finding the inverse. So just go ahead and find the inverse even though it's not a function.